Hey guys, let's get through some of these probability distribution notes. See how far we get along. Okay, so before we talked about probability. We were considering sort of events happening in conjunction with other events, maybe. So these are joint probabilities, or we also sort of find the probability of something else happening. How does that influence something else? So this is a conditional probability. Now we're going to talk about sort of how to think about probabilities within the realms of distributions, right? So in statistics, we're really concerned about the distribution of sort of data, and now we want to know, what's the probability of some event happening within our data, right? So I think the first day of class, or one of the first assignments, we talked about how what's the probability of somebody showing up to class the next day who's like really super tall. And based off of the distribution that we already have. So these are the kind of questions that we're addressing, right? So here's a few that we might think about. Which set of investments will minimize risk? What's the chance that Amazon.com visitor will buy at least one book? What's the probability of an error in the first exam that I write? According to the U.S. Census, 1/3 of all businesses are owned by women. We randomly select 25 businesses. What's the probability that 10 or more are owned by women? So this is the first step in helping us sort of being able to develop and test theories. And we'll see this in the next few weeks, that we first have to learn how to draw probabilities from distributions. And then that's really going to help us in a few weeks again to help us understand kind of how to test different sorts of different theories that we can base on distributions. All right, so what do we mean by distributions? Well, so far we've just talked about distributions in the terms of histograms, right? So we've been able to draw these histograms. Well, it turns out that there's more than one way to represent a distribution. So we have tables, charts, and equations are the different ways. So tables, well, we've actually sort of seen tables with sort of bins. Remember when we make a histogram, we get these little bins, and then we can see how many are in each of these bins. So this is what we mean by tables, is sort of just separating the data, and then sort of showing what percentage is in each sort of chunk, right? Remember the bins, we do that with histograms. Separating the data. So charts, so this is just sort of histograms, right? So we're going to play around with that some more. It's going to help us understand what we mean by taking probability from distribution. This is the new one, though, equations. And equations, well, we don't care too much about in this class what to do with these equations. We just know that they're there, and they help us sort of understand some of these distributions in a sort of a more formal way, right? So this just is sort of for convenience sake. For convenience. I'm pretty sure I spelled that wrong. Convenience sake. And I'm going to show you some of these formulas, and they're going to kind of freak us out because they're kind of crazy formulas sometimes, but that's okay. Just help us understand what's going on with some of these distributions from a mathematical standpoint. And then in the background, how we figure out these probabilities will just be done sort of without us even knowing what's going on. So first, let's talk about how to define an event in a distribution. So we're going to talk about in terms of what we call random variables. So think of a random variable as just an outcome of something happening, right? So we want to see what's the probability of this happening, right, given that we know that there's some distribution that's underlying. Two types of random variables. First, we have these discrete random variables. And when we say discrete, we mean countable numbers of values, right? So, for example, the number of defective items in a production batch is a discrete random variable. I have a list of some of those. Here we go. The number of lights left on in a house, right? So we're counting how many lights were left on the house. Number of defects in a product, that's this one. Number of electoral votes for a candidate. Number of people whose favorite ice cream is chocolate chip. The number of chocolate chips in a cookie. Right? So these are all countable things that we can count. So we're going to call these discrete random variables. And at some point we might ask, what's the probability of finding 25 chocolate chips in this cookie? Right? So we're counting 25. We know a sort of a distribution of each of these. So a couple of sort of jargony type things that we have to figure out here is we're going to call this discrete random variable x, right? We're going to call it capital X, and it has an associated probability mass function. We're going to call it probability mass function, PMF. Probability mass function, f of x. That's how we read this, f of x, where f of x equals the probability of this big X equals some small x. Right? So this is going to make sense in a sentence, but in a second. But this is basically saying, like, again, to my chocolate chip cookie, what's the probability that big X sort of the chance that there actually is 25 chocolate chips in a cookie, right? So this is the cookie, here's 25, something like that, right? In other words, for a discrete random variable, the probability mass function is just a probability, right? So just think of this f of x thing, it's just a probability, right? F of x is just a probability, so nothing really new here, really. In fact, there's these two rules that we already heard, is that this f of x, or this probability, has to be between 0 and 1. We know that, we did this last week, no problem. And if we sum all of these f of x's up, all of these probabilities of x, that they have to equal 1 collectively. Like, if we add them all up, they have to equal 1, right? So this is not new, we know this already. We're just going to call it something a little bit different. That's okay. So the random variable x has a cumulative mass function, so this is a little different. Cumulative, which means just what you think. It means we're going to add them up as they go along. Also called the distribution function of x, where f of x equals the probability of sort of big X is less than or equal to small x, right? So we're going to add everything that happened smaller. So I got an example here. So assume that x, here we go, assume that x is the number of cars sold in a day. So we have a car dealership, cars sold in one, let's see if we can do this a little better, in one day, right? And we know from past sort of research that we can only count on selling up to 4 cars, right? So we're just going to make a column of x's. We can sell 0 cars in a day, we can sell 1 car in a day, we can sell 2 cars, we can sell 3 cars, or we can sell 4 cars. And we've never, ever in history sold more than 4 cars in one day. So we just know that that's sort of the upper limit. That's okay. And then we can come up with sort of the f of x. Remember, f of x is just the probability of the x. F of x for each of these x's. And we do this from sort of past data. We know that 20% of the time we sell 0 cars, 30% of the time we sell 1 car, 30% of the time we sell 2 cars, 10% of the time we sell 3 cars, and 10% of the time we sell 4 cars. Let's make sure that equals 1. So that's 50, 50, that's 100, right? So if we sum all these f of x's up, we sum them up, this equals 1, right? So that's happy. Now we can do this cumulative function, f, capital F of x, right? So that's the only difference between this and this is this cumulative, right? We're just going to add everything above it, essentially. We're going to see what we want to know is everything that's sort of smaller than a given item. Well, if we just start with 0.2, nothing can be smaller than 0 cars. We can't sell negative cars. So that's good. And then from here, the f of x would be the capital F. Everything smaller than or equal to 1. Well, that's this number plus this number, right? So that's 0.5. And from here, we just add the next one below. So this is 0.8. This is 0.9. And this is 1. So this is going to come in handy when we ask questions like, all right, what's the probability of selling, at least 2 cars, or at least 2 cars? Well, that means 2 or less. At least car is 2 or more. So let's think of another one. That we sell at most 2 cars. That would be better. If we sold at most 2 cars, that would mean 2 or less. Well, we can immediately say, well, that's 80% chance that we sell at most 2 cars. All right. If someone comes and says, what's the chance that we're going to sell 3 or less cars? Well, that's 90%. So that's why we have this cumulative. It's really nothing special, but it just helps us answer some of these questions in another way, a little bit easier. All right. So let's move on. All right. So that was discrete, right? Discrete variables, we're going to count them. So continuous variables take on continuous interval values for which there's infinite number of possibilities. For example, the width of an extruded bar, right? I have some other examples. If you're making an extruded bar in some factory, the width of that thing, depending on how precise we measure it, can be a continuous random variable, right? So here's some other ones. Time it takes to take a timed test. Right, depending on how accurate my sort of stopwatch is, I can get into sort of milliseconds or even more precise. Air pressure in a compressor, weight of a cereal box, amount of rainfall, amount of water in a pool. So these are all things that I can measure very precisely, and I can have an infinite sort of number of values. So counting them doesn't help. I just have to have sort of more precise values. This is a continuous random variables. And we're going to call these a little bit different. Probability density function. You should click on this link. It's going to be fun. Density function. and it's really similar, but in our notes here, we're gonna, instead of using x, we're gonna use y. Don't get confused, but we're just gonna use y because we're thinking about continuous variables. So we use the same thing, right? So we have y and then f of y. The PDF is a graphical representation of this frequency. This is a histogram, essentially, right? So it's not a probability, but it's used to help us find probabilities. The probabilities that a continuous random variable is exactly equal to the single value is 0. So this is interesting. A continuous random variable is exactly equal to, so if I say, okay, I have a continuous variable, and I ask, what's the probability that, let's see, the weight of the cereal box is exactly 10.3 grams. Exactly 10.3 grams. Well, the answer to that is 0. I can never have an exact probability for some continuous variable. And the reason why is because I can be really precise, right? Like, well, it was actually 10.3 3000001, so that's not the same as 10.3, right? So that's why, is because there's no way that I can be exactly precise. Continuous, by definition, means that there is no sort of precision in here, that it's just sort of a continuous line. And we're going to see in a minute that's the case. So instead, we take intervals, right? So we would ask questions like, what's the probability that the weight of my box is between 10 grams and 11 grams? Well, I can answer that question. I can see what's in between those two, but I can't answer the question that's exactly one number. So we'll see that in just 1 second. Here we go. Requirements. Each value of this f of y must be non-negative. The total area underneath has to be y. So these are the same thing. It has to be equal to 1. These are the same things we already know about, right? It's got to be between 0 and 1. It can't be non-negative. And it has to sum up, the total area has to equal 1. So here's an example of what we mean. So far we've been sort of really abstract, but let's get in a good example going. Example. So let's go back up here to this. Suppose that y, we're at a factory and we make these extruded bars, and it equals the length of extruded bar. This extruded bar is used in a car or something, right? So it's something that some part you put in the car, and we have to go and measure the length. We have a specific sort of desirable length that it has to be, and we go and measure it. And we know that, for some reason, we know that this is what we're going to call sort of, it's the distribution of this looks something like this. Let me show you. So it's between 12 centimeters and 15 centimeters. Right, so this is our y. And the probability, f of y, so we're going to have over here, f of y is the same between any value between 12 and 15. So that means it doesn't matter. There's no sort of one point that's more or less likely. We just know that it's equally likely between 12 centimeters and 15 centimeters. Right? So that's what this picture looks like. So this right here is some point that we can find, and we can say that everything underneath this area, everything in the box. So actually, we say the area. The area of the rectangle equals 1, right? This is a probability. So anything inside this rectangle, if we sum it all up, it has to equal 1, okay? So then we can ask questions like this. Well, what's the probability of something that's between like 13.2, and I don't know, maybe 14.7, right? So we can answer this question. These are the kind of questions we're going to ask. Okay, so we want to say, what's the probability that a bar that I make is inside here, right? What's in between these 2 points? Well, if this whole entire rectangle equals 1, then I just find the area of this smaller rectangle and divide it, right, by the entire area, and I have the percentage, right? So this is kind of the same idea of the probability that we looked at in a second. So we're going to answer questions just like this in a second, but this was to help us understand what we mean by coming up with probability sort of charts, probability distributions that are graphs, right? So this is it. We're going to draw it graphically and say everything that's within, sort of underneath a certain area, that has to all sum to 1, right? That's what that means. And then if I take a certain proportion of it, I know that the other leftover proportion is whatever's left over of 1. Okay? So that's where we're at with this. Okay, so let's talk about some common probability distributions. There are several, way more than we're going to cover in this class. We're actually going to cover 3. The book covers several more if you want to look into some more. And later on in some other classes, you might be introduced into a couple others. So we can talk about those in class maybe. But we're going to talk about the uniform distribution, which is continuous, a continuous distribution, a normal distribution, which is also continuous, and then finally this binomial, which is a discrete distribution. So the uniform distribution is what we just saw. It's an equal chance for a variable to take any value between 2 points. So this means that taking an average is sort of meaningless, right? So an average isn't going to really help us because, well, it's equally likely between any points, which means there is no mode, right? Everything is just as equal as anything else. So maybe the median helps us where the middle is, but other than that, it's not going to give us a lot of bang for our buck. So here's an example. The amount of gasoline sold daily at a service station is uniformly distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons. Okay? So this is sort of, uniform distribution doesn't come up a ton. A ton does sometimes, but this helps us understand intuitively what's going on when we're going to try to answer these probability type of questions. All right, so here is sort of the simple explanation of what's going on. So if we want to find the probability that some x falls between 2 points, in this case C or D, then it looks like this. So really, again, we're just finding the area of a rectangle, right? This is just the area. Whoa, start over. Area of a rectangle. So this is geometry. In statistics, we have to go and borrow things from all sorts of fields. Well, we're just borrowing ideas from geometry in this case, where we find the width of a rectangle and the height of a rectangle. And that's it, right? So that's all we're going to do. So in this case, we say we can find the total width. Well, it's just sort of B to A, right? That's it. And then to find the height, well, that's a little tricky. But if we know that this is uniformly distributed, that there's equal chance between these two, and we know that the total sum of everything in here, this width times height, has to equal 1, right? Well, then it's just 1 over b minus a. And we can work out the math if you want to, but it is, right? It's okay. So that's the way it is. It's 1 over b minus a. That will give us the height here. So if we want to find the probability of something, between c and d, it just looks like this, right? D minus c times 1 over b minus a. Actually, I would prefer to write something like this. This is even more simple for me. D minus c over b minus a. This is the same thing, right? I just sort of put this d minus c into there. But this makes sense to me because this is just saying, since these are uniformly distributed, it's equal chance across these things. This is saying, here's my part. This is the probability, and I want this as my numerator, and my denominator is just the entire part, right? So here's my numerator, here's my denominator. This is just a fraction. This is just a probability that we're used to dealing with. So nothing mind-blowing here. But what we're really doing, this sort of shows us that, is finding the area of a rectangle. And we're going to figure out how to do this in a second. So here's an example. So we're going to use this same gas station example above. So find the probability that the daily sales will fall between 2,500 and 3,000. So we're going to use that same data. So let's first of all write this out in probability notation. So I would write probability, right? So that's a P probability that we have some x, right? It's going to be between two numbers. So I'm just going to go ahead and put, my inequalities, something like this. It's going to be, it says in here, between 2,500, all right, so 2,500 and 3,000. And then, given what? Well, first of all, sometimes, and we're going to see this all these, we can write a uniform distribution in shorthand like this. We write the U, that just stands for uniform, and then we say sort of the upper, comma, lower value. So if you see this U, some number, comma, some number, that means this is a uniformly distributed variable between some, actually, I reversed these, it should be the other way around. Lower, comma, upper. I kind of screwed those up. So you should put lower first and then upper. So this would look like this. Uniformly distributed between, what was it, 2,000 and 5,000, right? 2,000, comma, 5,000. So what is this saying? This saying, I want to find the probability that some x is between 2,500 and 3,000, given that I have a uniform distribution between 2,000 and 5,000, right? So that's all that we're saying right here. So this given over here, this is a conditional probability, but we're not going to deal with something crazy like we've done before. It just means that this is our condition. This is what we're thinking about. This is the distribution we're considering. And now we want to find out the probability here. This tells us everything we need to know to answer this question. So first step, draw a picture. So let's draw this picture. Whoa, here we go. So first draw the picture of the entire piece. So here's 2,000. And let's say here's 5,000. Alright, so this is x, and this is f of x, or y and f of y. It doesn't matter. Use x or y sort of several different times in this set of notes, so it doesn't make a big difference. And it's uniformly distributed, so we know it looks something like this. We could figure this out. This is actually 1 over b minus a. Where I got a meaning, looks like b minus a. Which equals what? Well, that equals, well, what's b? So b is right here, and this is a. Scroll down just a little bit. Okay, b, and there's a. Oh, ew. B, here's a. So what we got? 1 minus 5,000. Oh, over 5,000 minus 2,000, which is 1 over 3,000, right? I'm running out of space, but you should write 1 over 3,000. What's going on right there? And then the question we're asking is between 2,500, so let's just make up a spot. Here's 2,500. And here's between 3,000. This isn't to scale, but that's okay. Here's 3,000. And what we want to know is what's the probability of daily sales are going to be between those 2 points, right? So we're just going to color this spot in the middle. And this is going to be our numerator, right? So let's just write this out. How would this look like? Well, according to the formula before, you would say something like this. Equals, 3,000 minus 2,500. Right, that gives us our first one. So this would be D, and this would be C. So D minus C times 1 over B minus A. 5,000 minus 2,000. Oops, so this would be bigger. So, but we already figured out that you could actually do this all at once. So 3,000 minus 2,500, well, let's just do this fast. 3,000 minus 2,500 is 500. 500. And this down here, we know that that's 3,000. So that equals 16.6%. All right, 1 second. Okay, back. Sorry, we had a little interruption, and we're at a brand new location. You may have noticed that the saxophone lamp is gone. We are now in what used to be an office. It's now nursery, crib. That's what happens when you get children. You no longer get an office. Anyway, let's talk about this 16%. So what does this mean, 16%? So 16% chance, right? This is what we're looking at, the probability between these two numbers. Well, we could say that happens 16.6% of the time, essentially, right? So that's what's going on there. So that's the probability that daily sales will fall between those two numbers. Okay, so let's find the next one. What's the probability that the service station will sell at least 4,000 gallons? So at least 4,000 gallons. 1 second. Get my pen going. At least 4,000 gallons. So what does at least mean? Well, that means we're considered anything that's, at least, I was curious about anything that is smaller than that, or anything that's bigger than that. Anything that's bigger than that, right? At least is anything that's bigger than that. So we would write the probability that X is greater than 4,000, and at least usually implies, it does definitely imply equal to, greater than or equal to 4,000, which we'll find out in a minute. It doesn't really matter if we say equal to, but that's okay. Given, again, let's write this the right way, given that we have some uniform distribution that's uniformly distributed between 2,000, and 5,000, right? So remember that's what that U means. And then this is total bracket here. It's pretty ugly, but that's to match this other bracket. All right, so let's draw this picture. Oh, here's our little, sorry for such a bad axis, that's okay. Here's our square. This is supposed to be a rectangle. just imagine, if you will, that it is. This right here is 2,000. This right here is 5,000. And then we're going to find some point over here that's 4,000. Here it is, 4,000. 4,000. And remember, we call this axis x and this axis f of x, so lowercase f of x, f of x. All right, so we want to find this part that is greater than 4,000. So part of drawing this is to actually draw which, color in which side that you want. Well, in this case, we want this side, greater than 4,000, right? Color it in. All right, so how are we going to do that? Well, this one's a little different because it's not between two numbers, which our little formula was before, but it really still is, though. It's between 4,000 and 5,000. We know that 5,000 is as big as it can get. That's what this says. It has to be between 2,000 and 5,000. So we can do the same thing, right? So we can say, well, what's 5,000 minus 4,000? Right, and it's, again, if we just think of this as a fraction, is essentially the numerator. The denominator, then, is what? 5,000 minus 2,000, which is a bigger number. And so this ends up being what? 1,000 on the top over 3,000, which then equals 1/3, right? 1/3 or 33%. 33%. So what does this mean? Well, this means that this chunk right here is exactly 1/3 of the puzzle, and then this over here is another 2/3, right? Because this has to equal 1. These two pieces have to equal 1, right? So again, so the probability, according to this question, with a uniform distribution between 2,000 and 5,000, the probability that some variables greater than 4,000 is exactly 1/3, or 33%, 33.33%. Right? Let's be repeating. Okay, so let's do the next one. Maybe. Here we go. What is the probability that the station will sell exactly 2,500 gallons? All right, so what does this look like? Exactly would you say probably that x equals 2,500 gallons. So let's draw this one out. Let's see if I can do a little bigger. Oh, wow, that's a good straight line. Look how good that was. Just need a little practice. Don't screw up now. Okay, good. Good. Man, I should just go slower. 2,000 and 5,000, right? I didn't do this right. Remember, we should probably, and then we have to put in the given. Sorry, this should be given. Given what? Uniform distribution between 2,000 and 5,000. It's good practice to write these givens in. Oftentimes you won't see the given. But I think it's good practice. It helps understand. It's not just probability that 2,500. Well, it is. But we want to know. We want to say, well, according to this distribution, right? Given this is the distribution that we're following. Because we could be following all kinds of distributions. Who knows what it is. But this is the one we care about for this problem. So 1.5, exactly 2,500 gallons. So that's somewhere like, I don't know. Let's change colors here. Right about here, maybe. It's probably closer. My scales are always wrong. But that's okay. 2,500. Okay, and there is no sort of upper bound and lower bound. It's just 2,500. So in order to use our equation that we used before, it would be something like 2,500 minus 2,500 over, so that's our numerator, over 5,000 minus 2,000. That's our denominator, right? So it's just this line, the width of this line, which is 0, over 3,000. Which is 0. All right, so this comes back to this problem. The only reason we did this was to show that for a continuous distribution, like the uniform distribution is, there's no such thing as saying, what's the probability of an exact number? This sort of shows you why, right? Like it's exactly 0, because there is no width of this line. The same thing will hold when we start talking about the normal distribution. The same kind of thing goes in play. Because we can't actually tell this line is so minuscule. There is no width. There's no width, right? So we can't find any area. So that's that one. All right, let's pause for a second. All right, so that's it on this uniform distribution. Piece of cake. These are really easy problems. That really we just sort of find what the numerator is and what the denominator is, and it's just the area, right? It's just the space in between there. So let's move on here. We're going to talk about the normal distribution, which we already have discussed, right? So we know this empirical rule where we've sort of figured out this 68-95, where we can say if we go out certain standard deviations away from the mean, a certain percentage of all observations fall in there. So this is sort of the same idea. When we say percentage of, we're really talking about sort of the same thing as probability, right? The probability of something happening. But now we're going to take a different look and say, well, really what we mean is we want to say, what's the probability of some event happening in a normal distribution that's smaller than a certain amount. So all the way from sort of negative infinity out to our point, essentially where we're at. So let's talk about this. So normal distribution is one of the most commonly used continuous distribution. And the reason why will come up in a couple weeks, but it's really because when we start taking samples from any kind of distribution, the mean of those samples, if we were to take samples over and over and over and over again, every time we take a sample, we take an average, and then take those averages and then plot those averages as a histogram, those will almost always become normally distributed. We'll talk at length about this in a couple weeks, but it's pretty amazing that this happens. This is actually the whole basis of inferential statistics, is because of what we call the central limit theorem. It's going to come up. Let's stop talking about it. Okay, so let's just figure this out. First of all, let's draw a little picture again of the normal distribution, just to help us get it. So remember, we all remember this. Oh wow, this is one of the worst normal distributions drawn of all time, but it's a bell-shaped thing. Doesn't look anything like the one I just drew. Draw a better bell. But if we split it right down the middle, we talked about this already. This is symmetric, right? Symmetric, which means half of the stuff is on one side and half is on the other side. Symmetric. All right, so we could say that there's 50% of all observations on this side and 50% on this side. And theoretically, these tails, which I didn't draw very well, these tails actually go to infinity on this side and to negative infinity. So theoretically, they go forever, right? But we already know that within after about 3 standard deviations, the chance of something happening beyond that is really, really small. It can happen, but it's really small. But just to remind us that that's the case. And then here in the middle we have our little mu guy, which is the mean. And it turns out for normal distribution, this is also the median and the mode. So all 3 of these things are the same thing for normal distribution. Mu is what this says, mu, right? All right, so that's good. So let's kind of move on down here. Next page. So here's our first equation. All right, so the normal probability density function can be expressed in this way. All right. Yeah. So first of all, let's sort of see. We just talked about this. It goes from negative infinity to positive infinity. So y can be in between these two. So that we can understand, no problem. These little ups, 8s on the side, it's infinities. So here we got some funky like e's. All right, we got pi, pi. But the ones we really care about here is this guy, right? We know what that is, and we know what this guy is. We don't really care a whole lot about what's going on here. But because we got this e and we got this pi, we're getting some sort of curve. So remember, pi is used when you express circles. So this is going to make the curves happen. And then e sort of helps out in that regard too. So this is something that if you're taking like a theoretical math-based statistics class, you're going to have to learn how to derive this, but we do not want to do that in this class, so we won't. All right, but here we got our mean, and then remember this guy right here, this is sigma. What does he mean? Sigma, he's the standard deviation. Remember that? The standard deviation of the distribution. So mu is the mean, standard deviation. So within these two things, and we'll see in a second, everything else is controlled. So remember, we talk a PDF, probably density function is a PDF. So that's what this is. A PDF is a symmetric bell-shaped curve. So it looks like this is a very better picture than what I drew. And so these numbers here just represent the distance from this point to this point, right? So there's exactly 34% from one standard deviation, from the mean to one standard deviation on one side. Right, and then another 34 on the other side. So before we talked about the empirical rule, we said it was 65 or something like that, right? Well, really what we meant was if we take one standard deviation on both sides, right? So this is doing the same thing. It's just saying, well, if we just look on one side and look on the other side. And notice that they're exactly the same, right? And if we go out, this is 0.1359, this is 0.1359. It's exactly the same. And why is that? It's because it's exactly symmetric. So I actually only need half of the distribution. And then I know what the other half is. There's no problem. I can figure it out. So that's just something to remember. It helps us think about things going on in the future. All right. Make sure I'm not missing anything. Yeah, it looks good. All right, so 2 parameters, mu is the mean, and the sigma, the standard deviation, fully describes what distributions look like in all cases. So here's a picture of a normal distribution, and all we do is change the mean. Right, so here's mean of 0 is black, mean of 1, blue, mean of 2. So you can see that they look exactly the same, they've just been shifted over. So that's all, a change in the mean just moves the whole thing over, right? It looks exactly the same, we're just moving stuff around. The second one is the standard deviation, and it controls sort of the profile of the curve, right? So sort of whether it's really pointy or whether it's really spread out. So all 3 of these are all normal distributions, right? And the first one, the black one here, is with 1 standard deviation. The blue one is with a half a standard deviation, right? So if I have a smaller standard deviation, the curve sort of shrinks in, and then 3 is with 3 standard deviation. It kind of spreads out a little bit more. So this 3 doesn't look bell-shaped, but it still is, right? It still is symmetric exactly, and all the same things that we found before are the same, right, as far as the number of standard deviations away. It just means that it's spread out further. All right, so you may have taken a stats class before where you have tried to figure out the probability of something happening in a normal distribution, which we're going to do in the next page. And the traditional way to do this is to find a z-score, which we figured out how to do week 1 in our class. So we know how to do a z-score. It's just some x minus the mean divided by the standard deviation. And what is the z-score? It means how far is some point away from the mean in terms of standard deviations, right? In terms of standard deviations, right? And it can be negative or it can be positive. And what this really does, though, and we didn't talk about this, is it actually standardizes any point you have for any normal distribution. Standardize, what does that mean? Standardize means it puts it into a normal distribution that has a mean of 0 and a standard deviation of 1, right? So we could actually go through and show this mathematically, but we don't care too much. This is what it does, and this is actually kind of cool because then we can look in the back of any book that we have, right? Any textbook, any stats textbook for that matter, and find what we call a z-table, and the z-table will give us probability. So we're going to do that in just a second if I can find my textbook, which I probably left in my saxophone office. Yeah, we'll find another way to do that. That's okay. So, however, we'll show you how to do that. But really, Excel will just do this for us like a piece of cake. We don't have to convert it into a z-score. We just do it. So I want you to learn how to do it the other way, most likely because in other classes, you're going to have teachers who are going to say, go find the z-score or something like that. And you're going to need to know what that means. However, you should just do it in Excel. Yeah, there you go. You know my preference. So that's all there is to it. So this is how it's going to look in Excel. Let's see, I'm pretty sure I skipped over some stuff. No, not yet. Okay. So we're going to, let's draw a normal distribution right here. Whether we use the z-score or the Excel, this is what's going to happen. All right, so we have this normal distribution, something looks like that, only it looks better than that one. And here's our mean, right, mu. And then we're going to give it some point, right, for a z, like let's say a z of 1.2. That's something like right here, 1.2. And we're going to say, what's the probability? Well, let me just tell you, this is what the books give us. And so does Excel. It gives us the probability of everything left of that point. Right? I can't color so good. Let's get a thicker pen. Color everything left of some point. Right? So in the back of the book, if I go to a z-score table, which we'll do in just a second, and look up the value for 1.2, what it's going to give me is it's going to give me the probability of a probability less than 1.2, right? So it's going to say the probability that x, some random x, is less than or equal to 1.2, right? And then it's given, and then a normal distribution looks a little bit different. Normal distribution is an n instead of a u, but we do the same thing with mu is our first function and comma standard deviation, right? So just like with the uniform distribution, we put 2 numbers. It's the smaller and the bigger, and here we put the mean and the standard deviation. With those 2 things, we know everything we need to know about this normal distribution. So in this case, we say it's a normally distributed with mean of 0 and standard deviation of 1. This right here is what we call the standardized, the standard normal distribution, right? From 0 with a mean of 0 and a standard deviation of 1. if we know that, if we can say that that's given, then this right here is actually a z-score, right? So that's all that means. All right, so if we ask this question, then we're going to find the answer in the back of the book, or we're going to use Excel to find the answer. So no problem. So in Excel, how do we do this in Excel? And then we'll jump back to the book. We're going to do this back and forth all over the place. In Excel, we just take a normal random variable y with mean mu and standard deviation is sigma. We can find the probability of y is less than big Y less than little y by typing norm dist y sigma and 1. So this can work for any normal distribution. So I can put any mu in here and any sigma. I don't have to convert it to this guy right here, right? So that's why we like using Excel, because we don't have to do this conversion, right? It'll just automatically do this. By the way, I kind of skipped over this, but you could do this. All we're doing here is taking the area under this curve. This is calculus. That's all we're doing. So if you were really good, you could take our ugly equation up here. Where'd it go? Here it is, right here. And all we do is we take the integral of this from 2 points, right? So in the case of this one, we take the integral from -infinity to 1.2. And then we do it because we're really good, and then we can pump it out and we get the answer. Well, that's actually not that easy. This is a pretty hard equation to take an integral over, and so that's why things are printed in the back of the book, right? Of every single textbook for the past 100 years. So no one actually takes integrals of these anymore. And in fact, I wouldn't even try it if I were you. It's really ugly. And then for that matter, Excel doesn't even, again, the next step doesn't even make us put it into this standard normal. So that's nice. All right, so but here, even with the norm dist function, very important to draw pictures of probabilities, because the norm dist function only takes that left tail area, right? It only goes to the left, and we want other types of areas. So sometimes we're going to ask for something that's greater than, or sometimes we're going to take some sort of ranges. So that's important. So the other thing we can do is this function called norm inverse function. So the norm inverse function is just the opposite of the norm dist function. You can do this with a textbook too. It's a little bit trickier. But this is, and we're going to work a problem in just a second. This is the case where we want some percentile of a normal distribution. Say, I want to know the point of the 90th percentile in this normal distribution, right? So instead of saying I want to know the probability of 1.2, I say, well, I want to know the probability. I want to know what the point is if my probability is 90%, right? And then it will go and find the point for us, and it'll look something like this. So I tell it the probability, give it the mean and the standard deviation, and it will give me the point on the distribution. So what I mean by give me the point, so yeah, let's draw a little picture. I got to get better at drawing normal distributions. Here we go, normal distribution, and let's say we want to find the 30th percentile, essentially. So then we know the 30th percentile is like somewhere over here. All right, so here, let's say we want to find the 30th percentile. So what that means is that this thing I color is 30%, right? 30% probability, or 30% of this entire curve, right? This entire curve, everything under this curve equals 1, right? If I sum it all up, equals 1. So what that means is this other chunk over here is 70%, right? So this 30%, this is 70%. If I put it in this norm inverse function, it tells me the value in terms of my x, right? If this is x of this point, right? Whatever that point is right there, it will tell me what it is, right? So this sometimes comes in handy. We have a problem coming up that hopefully will help us solidify what this means. So here's some examples. Suppose that a gas station, so remember our old gas station that was uniformly distributed. Now we're going to say, it's actually normally distributed with a mean of 1,000 gallons and a standard deviation of 100 gallons. So how do we write this? In shorthand, we say normal distribution with mean of 1,000, comma, standard deviation of 100, something like that. So this is our shorthand, just to help us remember. The station manager just opened the station for business and notes that there's exactly 1,100 gallons of regular gasoline. All right, so he knows that any given day, the amount of gas that's used is a little bit different. It's normally distributed. So sometimes it's less, sometimes it's more. On a really good day, he's going to sell a lot, and on a not so good day, he's going to sell less. And so he wants to know whether he's going to have enough gas, because he's not going to be able to refill until later in the day after the business is closed. So essentially, he wants to know, is there enough gas to satisfy today's demand, right? So this question is sort of hard to tell, in this in this description, and usually it'll be less vague than this, but really what he wants to know is the probability that he's going to run out of gas, right? So, well, really, we could do that, but to start out with, let's ask the probability that he won't run out of gas. So how would we write that in terms of our notation? We would say the probability that x is, less than or equal to 1100. Oops, 1100. Right? So that's the same as saying, this would be 1100. That's the same as saying he's not going to run out of gas. What's the probability that he's not going to run out of gas? Right? That there's going to be enough in his tank to get through. Yeah. So and sometimes it's going to be on the right side, other times. And then let's finish off. Given, we'll draw in a picture, a normal distribution n of 1000, 100. Okay. Let's draw this. See what it looks like. Okay, here's my normal distribution. Oh, wow, that one was not very good. Here's my mean. What was my mean? Well, my mean is 1000. And then I have some standard deviations. I know there's one about there, and there's one about there, and there's one about there. These are standard deviations away, right? And actually, I know here the standard deviations are 100 away. So this one is what, 1100? This one is 1200. This one is 1300. And then I'm going this way. This guy's 900, 800, and 700. All right, so what is it I'm after here? Well, I want to know the probability in this, in this picture of x is less than 1100. This would be 1100, right? That's what's in our problem. 1100. 1100. Well, let's find 1100. Here's 1100. Draw the sort of line straight up. And I want to go less than, so this is how I remember. I look at the little arrow, which way it's pointing, right? It's pointing to the left. So then I know I can just fill in the left. That's what I want. Less than. So you remember in kindergarten or in elementary school, you learned about the alligator. Whatever it's eating, whatever's bigger. This is the same idea. All right, so this is what we're after, right? We want to know the probability of this side. Okay. So how do we do this? Well, it's a piece of cake in Excel, so let's write this. Let's change colors here. In Excel, we can do this easy. So we just type equal, and then write the word norm dist, right? And 2010 is norm.dist. It's exactly the same, no problem. So they're both the same. You can do both in 2010. And then we're supposed to put in some x, some mean, and some standard deviation. So the x here is, the point right here, 1100. So our first term is 1100. Comma, what's our mean? 1000. Comma, what's our standard deviation? 100. And then we just have to put in this number 1, right? This number 1 just tells us that we want a cumulative distribution, which means cumulative from negative infinity all the way to our point, right? Cumulative. We'll never not put 1 for normal distribution. So in some other times we might put a 0 in here for a binomial distribution in a minute, but we're never not going to put 1 for norm. So always put 1 in here. Or you can type in, I think, true. It's the same thing. All right, so this gives us an answer of point. You should try this, but I'm not going to do it now. 0.8413. So you should pause the video, go try this. Make sure you can get this right. So after you pause, what does this mean? Well, this means that this chunk over here is 84.13% of our entire area under the curve. So by default, that means this is whatever's left over, right? Which is another 16% or something, right? So approximately 16% over here. 1 minus this gives us how much is left over here. So we could say, actually from this, we can say, well, there's an 84.13% chance that you're not going to run out of gas. Equivalently, we could also say that there's a roughly 16% or 1 minus that percent chance that you will run out of gas, right? That's exactly what that means. Is that if we have a normal, if our daily gasoline demand is really this, and you really only have this much in there, then we can say what we just said. So very cool. So now let's do this with the Z table. I'm gonna have to pause and go find a Z table. 1 second. Don't go anywhere. Okay, I'm back. So let's figure this out with the Z table. I got one prepped and ready for us to look at. First, we have to convert this, though, into a z-score, right? This 1100 into a z-score, because we're in the wrong distribution. In order to use the z-score, we have to convert this into a normal distribution with mean of 0 and standard deviation of 1. Well, that's a piece of cake. So how do we do that? Well, let's see, with a z-table. First, make a z-score. So first step, find the z-score. Find the z-score. You could probably figure this one out in your head. You've probably already figured this out. So anyway, how do we do this? We find, if you remember, it's our x minus mu over sigma. So in this case, this is 1100 is our x minus 1000 is our mu over 100, which actually just comes to what? That equals 1. So that's, well, look at the picture that we have over here. It's exactly 1 standard deviation away from the mean, right? So like here's 1000, and we decided that each of these marks is a standard deviation. Well, here's 1100. It's right exactly out there. There's no, it doesn't have to be there, right? So this is a simple version just so that we can play with it. So once we know what the z-score is, then, so here's the z-score. Z-score equals 1. Then really what we're going to do, we're going to change this to, now we say, well, now we know the probability, and then we can rewrite this. The z is less than 1, and we don't have to say a given, because if we were talking about z's, then everybody knows that we mean a standard normal distribution with the mean 0 and standard deviation of 1. But we could write this of given n 0, 1, right? But it's the same thing. So this is now equivalent. It's the exact same thing. Those mean the same thing. So then what do we do? Well, we find our, we can look in the back of the book. This is there. Or we find it, we just Google z-table. That's what I did. And I found this. So this is thanks to Illinois State University, Econ 148, Applied Economic Statistics. So how do you read these? So over here we have a z, right? That's what this is, a z. And it goes from, this one goes from negative 3.4, and then it goes all the way to positive 3.4. Remember, a z is just the number of standard deviations away from the mean. And we know that there isn't much chance of something bigger than 3, in this case, bigger than 3 standard deviations away from the mean. It doesn't happen very often, so that's why this doesn't get much bigger than that. And then what's along the side here? Well, how we read this is like this one would be negative 3.4, and then if you want to go out several decimal places, you just do it out here. So this would negative 3.40, negative 3.41. We just find the intersection of there. It's negative 3.41. If we have, like, say we have, if we want to find a z-score of 1.62, how would we do that? Well, we first find 1.6. Here's 1.6, and then we go to 2 right here. 1.62 is right there, I believe. Yep. All right, so for our problem, we find the z-score of 1, right? So then we just want to find what the equivalent of that is. Well, we just find 1. Here's 1. 0.0000, that's what we want. So it's right here, 0.8413, which is exactly what we found with Excel, right? 0.8413. So we're golden there. All right. All right, so that's cool. So if we want to do a z-score, we first have to convert our x into a z and then go look it up on the table. But we have to remember that just like with the norm dist function, it only gives us what's left. So it's the left of the table, the left tail side, right? So from negative infinity into all the way up to our point. Right, so let's look, I think the next set of notes is going to sort of talk us through how to do this if that's not the case. Actually, before that, let's do this inverse function. At what amount of gas can the manager be 95% sure he won't run out, right? So this is this inverse function that we're thinking about. So now the manager's sitting there saying, "Oh, that's pretty bad. I have a 16% chance of running out. That's really pretty bad. How much gas should I have sort of in the end of the day every day where I know that 95% of the time I'm not going to run out?" So this might come in handy, for those of you who do lots of supply type of stuff. This is how we make sure that we have sort of the right amount of things. It's the same kind of problem. So in Excel, how do we write this? Well, this is a piece of cake in Excel. Again, if we have this normal distribution, what was it, of 1,000, 100. Well, then we just say equals norm inverse norm inv. We put in our probability we want 0.95, comma 1000, comma 100. And that's it. So plug that in and see what you get. I didn't write it down. So let's just do it real fast. I think I got Excel open here somewhere. Oh, what is this? This is like your final exam. Huh. I think we better do this somewhere else, huh? Okay. Oh. Okay, so let's do it right here. So equals norm inverse. There it is. Whoops. Norm inverse. 0.95 is our probability. The mean is going to be 1,000, and the standard deviation equals 100. Enter. 1,164 gallons. Okay. 1,164 point something gallons. So he's actually pretty close. What did he have? 1,100 gallons? So he's only about 64 short of being 95% sure he's not going to run out of gas. 64 gallons. So that's really only like that's what, like 3 tanks, maybe 4 tanks of gas, right? So he's only about 4 cars short of being 95% confident. So maybe he doesn't feel so bad anymore. Okay, so that's how we answer these kinds of questions, norm inverse. Again, we can draw this picture to see what this means, right? Wow, bad picture. We say we want to know what this point is right here, such that everything to the right is 95%. Everything to the left, sorry. Everything over here is 95%. Color this all in. This is 95% of the time. So again, and then by default, whatever's left over here in this tail, this green area, is 5%, right? Because everything has to sum up to 1, right? So this inverse function is going to tell us, though, let's say this axis right here is gallons of gas. The inverse function will tell us what point right here is such that 95% is left and 5% is right. This is how we do that. Okay. All right, so let's move on a little bit. So 3 types of problems that we run into. So first one, find the probability that's less than some point. This is what we've already done. What's the probability of selling less than 1,100 gallons of gas? Well, let's just draw a picture real fast. So here's 1,100. 1,100. And we care about what's to the left of it, right? It was less than 1,100 gallons. Less than 1,100 gallons. It looks like this. So we know how to do this. This is just the regular norm dist. This is what norm dist gives us, or this is what the z-score tables give us. Z-score tables. Okay. So back up here, what's the probability of a greater than some point? All right, so what's the probability of selling more than 1,100 gallon gas? Well, we actually solved that earlier. How did we do that? Do you remember how we solved that? Let's zoom up a little bit. It was up here. We decided it was 16%. How did we do that? Do you remember how we did that? Oh, yeah, I remember. We took this 84.13, 84%, and we just subtracted from 1 minus that, and that gave us 16. Because we remember that everything underneath this curve has to equal 1. Ah, okay. So we can actually do that. So we can just solve this, and then just say 1 minus that, and it gives us this, right? So that's exactly what we're going to do. So let's draw this picture. First, see what we mean. Man, my normal distributions are getting worse. Oh, whoops. That's okay. This is our mean. Here's 1,100. 1,100. But now my problem, and I got to make sure I read the problem and know what I'm being asked, right? Because if I don't realize what's being asked for, I'm going to get the problem wrong. So make sure I draw the picture and say what's the probability of selling more than, selling more than. So this is a probability that x is greater than 1,100. So here, look which way the arrow is pointing, right? Greater than. This is an arrow. You can think of that. Arrow is pointing that way. That's the side of the distribution I care about. Greater than here. All right, so if I'm going to do this, how do I do this? Well, in Excel, I just say 1 minus, so we figured this out earlier, norm dist, and then we do it just like we did before, 1100, comma, I'm going to write a space, 1000, comma, 100, comma, 1. Look at that. And this should be, we figured this out approximately, I think it's like, it's going to be less than 16%, but around 16%. So you should try it and figure out what it is. Should be around that. So what does this mean? Well, let's break this. This norm dist right here, this is what we just did, right? And then we just take 1 and minus that. Because remember, everything under this curve has to sum up to 1. So this part is just what's ever left over. So this is just how we do it. And we do the same thing with the z-score. So if we're going to do the z-score method, z-score, then we say, well, we go find the z-score, and we say 1 minus the z-score. Whatever gives us on the z-score table. Not 1 minus the z-score, but what gives us on the z-score table. Z-score table results. All right. Finally, last one. Find the probability that something is happening between 2 points. Let's try this out and see what I mean by this. All right. Here's a normal distribution. Here's 500 gallons. And here's 1,300 is probably over here somewhere. 1,300. So what's the probability of selling between 500 and 1,300 gallons? So let's color this in between, right in the middle. Now this one's a little trickier, but it's not too bad. So we just sort of have to think about, again, this is sort of geometry, so think about how do we figure out the area under the curve totally has to equal 1. And we can say from here, from negative infinity to here, we can figure that out. Right? And we can also figure out from negative infinity to 500. And that's the part we don't care about, right? So let's clear this. We actually want to erase this. We don't want that part. Right? So don't want the red. Okay, what I colored in red, right? We don't want that. So how can we do this? Well, we can find everything left of 1,300, and then from that subtract everything left of 500. And that what will be left over is just this part in the middle. So that's exactly what we do. So we say equals norm dist. Oh, we gotta help her. She's coming to help us. Come over here, Nora. Say hi. Norm dist of 1,300, comma. This is what we do for fun at our house. 1,300, comma. What was it? 1,000.
Yeah.
Comma 100. And from that we subtract norm dist. Just a second, buddy. I'm almost done. 500, comma 1,000, comma 100. All right, so what is this going to do? This is going to subtract. We're going to go figure out this, basically this red stuff, and subtract it from all this gray. The gray is actually going to go from negative infinity to there. All right, that's it. I think we're going to have dinner now.
Dad, why did you...
All right, dinner's not quite ready. So let's talk this through just a little bit more. We're going to do several of these next time in class. Actually do them in Excel. I'll figure out what this means. But hopefully this sort of helps you understand what's going on when we can ask these sort of questions if we assume a normal distribution. I think this next question we actually already answered above, so I don't know why, but for some reason in my notes it showed up twice. But so we just have to figure out what kind of question it's being asked, and then we just plug it in. It's just a plug and chug. So once we figure out how to use this norm dist function, there's nothing to it. This is really easy, right? All right, so that's the normal distribution. So the next topic is this binomial distribution. It's very similar, actually, the normal distribution. In fact, it turns out maybe in class we'll do a little experiment. We can find that the binomial distribution actually ends up looking very similar to the normal distribution. But what is first of all, what is the binomial distribution? Well, this is the case where we have something that has two possible outcomes for every trial, and then we just want to count. This is a discrete distribution. Right, discrete distribution. So that means count, right? That means we're going to count how many times a certain occurrence would happen, right? So here, for example, if we're inspecting finished goods, they can be classified as either good or bad, right? So we could also, anytime we have only two possible outcomes, So for example, our M&Ms keep coming up. We could say it could either be plain or peanut, right? If I have this big jar of M&Ms and there's only one of two possibilities, plain or peanut, that would be a binomial distribution. Well, that would be sort of what we call, yes, a binomial distribution. In general, though, we have to figure out what would be a success, right? And then we count the number of successes. So count the number of successes, and that is what we call a binomial distribution, the count of number of successes. So there could be, if I had this jar of M&Ms, and 50 times I pulled one M&M out at a time, and then put that one back in. I would count how many times I had a success, and I would define a success before I started. Maybe I would say the peanut M&Ms would be a success, and then at the end I could say, well, this is how many I had, right? So that number is actually distributed, right? If this is randomly generated, so that's what we have. So we have to know the probability of success. We're going to call that P. Right? And assume that P is constant from trial to trial. That means that I'm not pulling out an M&M and popping it in my mouth. It's actually the exact same probability every single time we do this. Right? So the M&M example gets sort of not so fun, but in a minute we're going to look at some other examples. All right, so what's next? 3 important assumptions for the binomial distribution. We have n independent trials. N independent trials. So we're going to see this n, this little n, right? This n again, n independent trials. So this is just the number of times I try something. So back to the M&Ms. Say if I pulled out, I wanted to pull out 10 M&Ms, the N would be 10, right? I pulled out 10 different times. Every time I tried it, I would be an experiment. So how many times did I experiment with something? There can only be 2 possible outcomes, and the probability of success has to be constant from trial to trial. So that's what we just talked about. All right, so this is just like the normal distribution has this. We can represent it as a formula. This looks amazing. So this n with this x underneath it actually ends up looking like this with these exclamation marks, which means they're really excited. It's like n x. No, that's not what it means. These are n factorials. So a factorial, if you remember what a factorial means, you probably remember this, but it means something like, let's say if I have a 4 factorial, remember what that means? That means like 4 times 3 times 2 times 1, right? So we just multiply everything all the way down to 1. We don't care too much about that, but that's what these factorials mean. So we got a bunch of factorials, and then we're raising things to the power of x, 1 minus p, n minus, we don't really care. So if we did care, though, we'd have to figure out, again, how to take an inverse of this and kind of figure out, we could create a chart and figure out the probability of all these things. Instead, you guessed it, we're just going to let Excel figure this out for us. And it's really easy. Once we figure out any of these dist functions, right, norm dist, binom dist, they're all almost exactly the same. So we can figure one out, then we can just kind of figure out the rest. There's others that we're not going to cover in this class, but they're very similar. In this case, we have x, right, so this is what we want to try. So we'd say, I know some probability, p, and I go run an experiment n times, right, and then maybe I get some x, right? And then I say, what's the probability of that happening? That's really what we're asking here. What's the probability of that happening? If there's only one of 2 things, right? And the p has to be the percentage of successes, right? And then this I is the final thing. It can be either 0 or 1. If it's 0, then we have an exact. So this is a discrete distribution, right, as opposed to a continuous distribution, which means that we're allowed to just say, what's the probability of our x exactly equaling something? We're allowed to say that. Where we couldn't do that with continuous distributions. Or we can let I equal 1, which then gives us back to this idea that we're going to look at the left side of something. Okay? So, side note, but for a binomial distribution, we find the mean of n times p. This is going to make a lot of sense in just a second. Or the standard deviation looks like this, n times p times 1 minus p. So that's just, we just believe that. Although this is very intuitive, and we'll see why in just a second. All right, so here is a problem. In a population of sales invoices, there's this sales voice population out there living and breathing in their own universe. 5% of them don't have shipping documents attached. What a shame. If an auditor takes a random sample of 50 invoices, so you can think there's this little population of sales invoices, they're just living in their little town, and then this big giant this big auditor, who's sort of like this big god, comes and pulls them out randomly. I could make a video out of this, maybe I should. 50 invoices. What's the probability that exactly 3 will have missing shipping documents? So that's our first question. What's the probability that there will be at most 2? And what's the probability that 5 or more will have missing documents? And then finally this question, what is the expected number of invoices with missing documents? So let's just work through these one at a time, and we're just gonna do it with the binomial dist function. All right, so the first one, first of all, we can write binomial dist functions in shorthand just like we did before. We use a b this time. Hard to remember these, comma n, comma p, where n is the number of trials and p is the probability. So in this case, what's our n? What's the number of trials? Well, we pulled 50, right? So we tried it 50 times. And what's our probability? Our probability is 5%. It's right here, 5%. 0.05. That's how we'd write it. So this is a shorthand for a binomial distribution with n trials with a percent of successes of 5%. So in this case, a success would be a missing sales invoice. So when we say success, it doesn't have to be good. A success can be bad. We just define whatever the success is, all right? It doesn't really matter. All right, so what's the first question asking? Well, it's asking the probability that x equals 3, exactly 3, given a binomial distribution with 50 trials, probability of 0.05. All right, so how do we do this? We just use this binomial dist function. Whoops, binomial dist function. And what do we put in here? We put comma, let's make sure we write this down, this 3, right? That's what we want to try. We want to see what the probability of 3 happening is. So this is what we put it in first. How many trials we got in there? 50, comma, what's our probability? 0.05, comma, and then we put in 0 instead of 1 because we want to know the exact, right? Exactly 3, which is allowed in this case. So this guy equals, I think it's 21.99%. You should go try that, but that's what I got. All right, let's do the next one. Probability this time, what's the probability that there is at most 2? What does at most mean? At most means less than 2, right? Less than or equal to at most. 2 is the biggest that's allowed. It can be less than 2. All right, so x then less than or equal to 2 given binomial distribution with 50, comma, 0.05. And all right, I kind of wrote this wrong, but this is exactly the same thing, right? Binomial dist, comma, or no, bracket 2, right? 2 is what we're after this time. 2, comma 50, comma 0.05, and then instead of 0 this time we say comma 1, right? And the difference is here we want to find the exact. That's what if we put a 0 in here, or we could write false in here, or we could write, for 1 we could write true, does the same thing. And this is because we want a cumulative, right? We want it to add up, less than 2, right? So if we were to draw this, again, here's our arrow, less than or equal to 2, all right? That's good. So what's the next one? It's probability of 5 or more. 5 or more. So probability, let's change colors. Probability that x is greater than 5 or more, greater than or equal to 5, given we have a binomial distribution of 50 trials, 0.05 probability of success. Well, this one's a little trickier, right? So this is greater than. So just like before, we can't actually just figure out greater than. But we could figure out less than or equal to 4. Right? And that should give us exactly the same thing. So remember, in this case, think of how many we could possibly have. Well, what could x possibly be? Well, x could be 0. It could be less than 0. It could be 1. It could be 2. It could be 3. It could be 4. It could be 5. In fact, it could go for a while here. But it can't be smaller than 0. We can have negative these things. And we can't have 1.5. Right? There's nothing in between. That makes sense, right? So you have to have exactly some exact whole number of invoices, missing documents. We can't have some fraction of. So what we want in this question is everything bigger than this, right? Everything bigger than this. But what the binomial dist function gives us is this part, right? However, we know that this entirety here, everything all the way until, who knows, until 50. This can go to 50, right? Can't get any bigger than 50 because 50 is the number of trials. All of that equals 1, right? If we just sum the probability, not x, but the probabilities of all of those, or what we like to call the f of x's, right? Of all of those, that equals 1. So this is like the 20th time I've said this. You sum these all up, they equal 1. So knowing that, then we can just say, well, if we can figure this part out, subtract it from 1, it gives us this part, right? So that's exactly what we're going to do. This is just like what we did before with the norm dist. So it's just 1 minus binomial dist, comma, but instead of 5, let's look at my picture. I actually want to look at 4, right? Because if I do 5, it'll include 5. Well, I want 5 to be included down here. So if I include 4, it'll find everything smaller than 4. Subtract 1 from that, which is what I got here. 1 minus that. Then I should be good to go. So 4, comma, 50, comma, 0.05, comma, 1, right? Because I want the cumulative. I want it all. And that'll give us, that's the right answer right there. And I think, actually I didn't do this before, the answer here is 10.36. And then I actually do have an answer for the one above too. It equals 54.05%. So we'll get some practice doing this in class the next time around too, but hopefully this helps you understand. So the last part, though, what is the expected number of invoices with missing documents? This one, we can actually just think about this intuitively. So if I have 50 documents, and from the past somewhere, I figured out that 5% have missing, or are expected to have missing shipping documents. Those are the outcasts of our population. So of these 50, how many are expected to have missing? Well, 5% of those, right? That's it. That's all that's going on. What's expected. So what is that? 50 times 0.05. Let's try that. 50 times 0.05. Which is, well, I don't know. 10% of 50 is 5. So this must be 2.5. Half of 10%. So I figured that out. So we expect that 2.5 of these should be missing. Well, we know that half. There's no such thing as a half of these. But that's what we say. We would call this an expected value. Expected value, which we also call the mean, right? That's the same thing. This is actually the average number of missing things. And why do I say that? Well, it is. But look at this. We actually figured this out earlier, or it was written here. Mu for binomial distribution equals n times 2. That's just what we did, right? We did 50 times 0.05. So this mu is completely intuitive. This is just the average or the expected number of ones that are missing documents. This guy is not quite as intuitive, but it's simple. We can just plug it in and go what's going on. Again, the same interpretation, though, that this is the standard deviation. It's the average deviation away from this mean. So we could plug this in and figure that out. So it's not too hard. We're not going to do it, but that's okay. We're taking a break. All right, it's almost bedtime, and I'm going to get kicked out of the office shortly. So let's finish up these notes. We're almost done. So we just finished with this binomial distribution. We're going to do several of these in class, so hopefully we get a little bit more practice doing this next class period. So let's move on. But we did finish talking about this expected value and variance. So probability distributions are summarized. Two measures, expected value, which is, we can just think of it as the mean, and the variance is the same as we've talked about it from day one. All right. So the mean is just the center of the distribution, and the variance tells us about spread. When we are talking about probability distribution, those quantities are population quantities. So that's why we talk about mu and standard deviation. So when we deal in when we deal in probabilities, we're almost always talking about populations. All right. So let's figure out how to do this with discrete variables. You can do this with continuous random variables, but you have to do a sort of integration with calculus. So again, we're going to not worry too much about that. We talk about when we talk about an expected value, we write it like this, e of x, right? So when you see an e of x, just think of mean, right? This is just a mean expected value, right? And what we're going to learn is this is actually, more specifically, this is a weighted mean, a weighted average. It's probably what you've heard before, a weighted average. So let's see how this looks, a weighted average. Expected value of x is the sum of across all x's of our x times an f of x. So remember this f of x right here, this part. This is a probability. And then this x, for discrete random variable, this is a count. Right, so this is a number, like 0, 1, 2, 3. It's a whole number. And then this is the probability of that whole number. Right? And then we do that for every single one, and then sum those all up, and that gives us our expected value of x. And down here, this is our variance, right? And the standard deviation, this is sigma squared variance, right? So what is sigma without a squared is the standard deviation. This is the sum, here's x minus mu, so we have to find mu. The difference from the mean for each x, remember this is a count. This is a count because we're talking about discrete random variables, so this is some kind of count, minus the mean that we calculate up here and square that. So the squared difference from the mean, and then multiply it by each of the probability. Oops, probability. And so this is sort of a weighted average of the mean, of the deviation squared, right? And then if we want to find the standard deviation, we just take the square root of that. This is a shortcut that we can do that also works, right? So if we work this all out, you get this. You just take the square of each of these counts, multiply it by the probability, sum those all up, and then at the very end we subtract the mean squared. It gives us the same answer. So we're going to show how to do that. So as before, the standard deviation, noted as sigma can also be used as a square root of the variance. So we know that already. All right, so let's work through an example. So at the very beginning of these notes, we said let's let x equal the number of cars sold on a lot. Number of, if we're a used car salesman, this is important. Number of cars sold on a lot in one day. Okay, and we came up with some numbers before where we decided, well, you could sell 0, you could sell 1, you could sell 2, you could sell 3, or we could sell 4. We decided that was all that you could do. And then we had a probability for each of these f of x, right? We decided that was a probability. So this is a discrete distribution. It's not a binomial distribution, although you could kind of come up with a binomial distribution this way too. But this is just a given discrete distribution, which means you just know this. It was just given to you maybe from past data, but we can't really, we don't have a good formula to describe what this is, but this is in a table form, right? So it's still discrete. So here's our f of x's. Right, so how do we find the expected value? So what's sort of the average value? Well, one way to do this is to we could kind of simulate this, right? We could go through and see a whole bunch of, like, maybe 1 million average days and then see what the average is. So maybe we'll do this in class, right? We could do this with Excel pretty fast, and I'll show you how to do it. That's one way to do it, but we can actually do it a little bit more theoretic way. And how do we do that? Well, we find this new column, x times f of x. Right? This is what the formula says. So we just take this x, whatever that x is, and multiply it by the probability. So let's do that for every one of these. 0 times 0.02, sorry, by 0.2 is 0. 1 times 0.3 is 0.3. 2 times 0.3 is 0.6. 3 times 0.1 is 0.3. And 4 times 0.1 is 0.4. And then we're going to sum this all up. And this sum will give us our expected value, when it comes up to be 1.6, right? 1.6. So this is what's expected. So let's draw this out graphically and see if this makes sense. So let's do a little chart here. We can say, look, here's 0 cars, here's 1 car, Here's 2 cars. Here's 3 cars. Here's 4 cars. And that was all we had, right? So, and then this is f of x. F of x. And it would look something like that. So here's 0 was 0.2. 1 was 0.3, so a little higher. 2 was 0.3, a little higher. 3 was 0.1, so smaller. Yeah, it should be even smaller. And 4 was 0.12, right? So what did we find? Well, we found 1.6, which is like right here, is essentially our average, right? 1.6, 1.6, our expected value, which makes a lot of sense. If you look at this, that actually looks right? Not quite 1.5, a little bit further over here. That's the balance point, right? This is the average. So how do we find that? It's just the weighted average of these. So if we know the probabilities of each of these happening, we can find the expected value, right? Expected value. All right. So pretty easy. So let's talk about the standard deviation. There's a few steps in actually calculating the standard deviation. So let's just write these out. I'm going to change colors actually. Steps for standard deviation. So this will be helpful if we kind of look back at the notes on the page before, and we'll write these out. So step number 1, we're going to create x squared column. All right, let's look at our notes up here and see why we're going to do this. So we're going to follow this guy right here. So first we're going to find this x squared column. Okay, so that's step number 1. Create x squared column. Step number 2, multiply x squared column by f of x column. Okay, let's see where that fits in up here. Let's see if we can look at it. All right, so we've figured out this x squared column. Now we're going to multiply by the f of x. Can you guess what the next step is? Well, we got to sum these all up. Right, so that's the next step. Sum the results. So number 3, sum the results. And then step 4. Step 4, we're going to subtract mean squared from this sum. Let's see what that looks like up here. So we're going to subtract mean squared, right? So we did all this. We found the x squared, we multiplied by each of the fx, we summed those all up, we got that done. Now we're just going to subtract mean squared from that. And since we're dealing with standard deviations, this was the formula for variance. Then the last step is to take the square root of all that stuff, right? So step number 5. Take square root. All right, so let's give it a try with our same data. So this is actually kind of done for us on the next page, which is nice. All right, so here's our x's, here's our f of x, here's our x squared. So this was what, step 1? Step 1. So I would do this in Excel, right? I would type these in Excel and these in Excel, and then this is just a formula that says this guy squared. Okay? And then here's step 2. Right? Step 2. Right, so I just take this number right here and multiply it by the f of x. Right, so this is x squared. This is f of x. And then at the very end, we're going to sum these right here. So this is what? Step 3. And then what do we do next? Well, step 4, we take the sum and subtract the mean squared, right? Which is, well, the sum right here is 4. We found right here 4. Minus, and page before we found that the mean was 1.6 squared. So that equals 1.44. And this is the variance. Right, we'd be done right here if we asked for the variance. But we want more, so we go step 5. And the standard deviation. Standard deviation. equals the square root of 144. Oh, what? Sorry, 1.44, which equals 1.2. All right. Cool. So this 1.2 is the same as we talked about the standard deviation before. We can think of this as on average, again, not quite right, but on average, the deviation from the mean of 1.6 is 1.2, right? So this sort of the spread around the mean is 1.2. All right, so this, these idea of mean and standard deviations come back from what we did descriptive statistics, although now we're trying to figure out how to do this when we have a probability distribution. We don't have raw data anymore, but we have a distribution of the probability. Then we can easily find this out. It's the same thing. It's nothing different. We think of weighted average. And the formula is pretty straightforward. Follow the steps for standard deviation. We can do it, no problem. And just know that this is just the sum. All right, so that's it for these sets of notes, I believe. Yeah. So we'll get some practice doing this stuff in class, and then some homework assignments doing this. Hopefully we'll get used to this. But the main topics of these set of notes that we're supposed to take away is that now we're going to deal with probability distributions as opposed to just probability events. The probability distributions can be divided into two things: discrete distributions or continuous distributions. Continuous distributions, well, we looked at two of those. We looked at the uniform distribution and the normal distribution. And then we also looked for discrete. We looked at binomial distributions, and then we looked at stuff like this that's on this page in front of me. That's these are just given discrete distributions, right? Well, someone will just give it to us. So these ones we can't sort of give a formula for. The ones that we have formulas for, we have really easy ways to do this. Either just find the area underneath the square, right? If it's a uniform distribution, we just find the area. If it's normal or binomial distribution, we use Excel to tell us what's on the left tail. If we need to find something that's on the right tail, we have to tweak it just a little bit, but it's not too hard. So once we get some practice doing this is really not hard. But we got to learn how to do this, because in the future, when we start actually doing some more experiments and actually testing theories, we're going to do this. This is exactly how we're going to test theories. Is we're going to say, look, here's the result from our theory, right? How does that compare to what we actually expected, right? And if it's like really not probable at all, then we would say, well, then something's different, something's wrong, something's not what we expected, and so our theory is maybe justified, right, or something like that. So we're going to get to that in a few weeks, but we got to learn these basics to get there. So get through these notes, make sure we kind of understand these notes. We'll get some practice doing this the next time around. All right, have a good week or weekend whenever you're watching the show. It's time for bed.